introduce our speaker for the evening. Dr. Claire Poppett is a researcher in astrophysics at the UC Berkeley Space Sciences Laboratory. She focuses on building instruments, so the tools that we actually need to put onto the telescopes to take data that help us learn things about the space, about astronomy. They're really important to helping us answer open questions. It's very easy to ask a question. It's much harder to figure out how to answer it. We're really lucky to have astronomers like her. And tonight I'm really looking forward to what she's going to tell us about dark energy, which is probably the thing in the universe that we know the least about. So please join me in welcoming Dr. Poppett.
Thank you. Thank you so much for inviting me here today. This is a really wonderful event, and it's the very last event of this season, so it's extra exciting. I'm a research scientist at UC Berkeley Space Sciences Lab. You can probably tell that's not where I started. I moved here a little over 10 years ago as a brand new postdoc to work on this new instrument that people were talking about. This is now known as the Dark Energy Spectroscopic Instrument. And in this talk, I'm going to start with a little bit of science. I'm going to spend a lot of time talking about the really cool instrument because it's my favorite part. And then I'm going to finish with some of our early science results, which are a little bit surprising and a little bit exciting. And people often ask me about my job and what my favorite parts are. And aside from the really cool telescope sites that I get to visit, the thing that really keeps me motivated is that I'm learning how to answer questions that I've been asking for all of my life. Questions like, how did the universe begin? Does the universe go on forever? If it has an edge, what does an edge to a universe look like? What will happen to it in the future? And what's the deal with dark energy? And when I started working in this field, I had no idea exactly what dark energy was. I knew it sounded really cool and really important. And when I started working more on this project, the thing that really drew me in is that nobody actually knows what dark energy is. And so being part of solving this big mystery was really appealing to me. And so before we start talking about things that we don't know about, we're going to start with things that we do know about. And so one thing we know is that the universe is very old. Does anybody know exactly how old? Yeah? Great, we're off to an excellent start. It's 13.8 billion years old. And how do we know it's old? And so there's a number of things that tell us this. We know that it contains old things in it. And so by radioactivity, we know that the Earth is about 4.5 billion years old. We know that the Sun is about 5 billion years old. And we know that some of the oldest stars that we can actually measure are about 13 billion years old. But the thing that really gave us a definite answer was by looking at the cosmic microwave background. And before we go too deep into the CMB, we're going to have our very first cool picture break. And so here's an image of a really old star. You can tell it's old because there's an arrow pointing to it. This is an image taken by Hubble. This star is called Arundel. And the current estimate is that it took the light 12.9 billion years to reach us. This means that we're seeing light that was emitted when the universe is less than 1 billion years old, or only about 6% of its current age. It's this tiny little dot here. And the reason that we can see it is because of a phenomena known as gravitational lensing. This means that there's a gravity in a galaxy in the foreground of this star, and it's so massive that it bends the light around it and acts like a big lens. So we can see this really distant object, and you can kind of see some effects of that lensing on either edge of the star. Okay, that was the fun stuff. Now we go to the cosmic microwave background. Okay, what is the cosmic microwave background? So it was initially detected by complete accident. There was two physicists, and they were trying to detect radio wave echoes with a really sensitive antenna. But they had this really weird background that they couldn't explain. It was there every single night, and it wasn't due to anything weird like a microwave in the staff cafeteria. but they knew that it was coming from outside of the galaxy. And at the same time, there was another team who had a theory that if the universe started with a Big Bang, then we should be able to detect the low-level noise that's left over from it. They found each other's research and realized that they had evidence for the theory of the Big Bang. This is an image taken by the Planck satellite. It shows temperature fluctuations imprinted in the very early universe. We know just before the universe became transparent, it was radiating like a black body, about 3,000 Kelvin. This is the temperature that hydrogen atoms can form. And if we could have seen that radiation right after neutral atoms formed, it would have resembled kind of a reddish star, like a giant fireball in the entire universe. And so we know it's a black body radiation. We're able to visualize it now in the microwave regime. And so by seeing that change in wavelength from red to microwave, we can determine the age of this CMB radiation. So we know that it's old. We also know that it's big. We don't know exactly how big the universe is, since we can only see light that's traveled since the Big Bang. The most distant objects that we can see are about this many miles away. It's a lot of zeros. It's about a zetomile, if you look it up. And so when you get to such large distances, miles aren't a very good measure of distance anymore. It's just too many zeros to keep track of. And so instead, we use the fact that light travels very quickly. It travels about 186,000 miles every second. And so light travels 6 trillion miles, and that's a unit of distance in 1 year, a light year. And so the most distant things that we can see are about 30 billion light years away. And so to set the scale, the sun is about 8 light minutes away. The nearest stars are a few light years away. And we can see things that are 30 billion light years away. And you might say, well, the age of the universe is only 13.8 billion years ago old. But remember, the universe is expanding. So the age of the universe isn't the same as the distance that the light's traveled to get to us. Okay, we also know that the universe contains billions of galaxies. The current best estimates are about 100 to 200 billion galaxies in our universe. Okay, cool picture break again. This is image. This is the Hubble Deep Field, released in 1995. Shows a patch of sky that's about 1/13 the size of the moon. They basically pointed at a blank patch of sky, and they just kept staring. And they learned that it wasn't blank. It was full of galaxies. This patch contains about 3,000 galaxies. Once you remove the foreground stars, you don't need to count them. And if you held a tennis ball at about 100 meters away, that's the size of the patch of the sky that we're looking at. It includes some of the oldest and the youngest objects that we know about. And if you thought that was a lot, this is the Hubble Extreme Deep Field. This is data collected over about 10 years. It's about 80% of the area of the original one, and it contains 5,500 galaxies. So we can see a lot of things. We can see a lot of galaxies, and we can see a lot of stars. But here's where it starts to get tricky. If you add up everything that we can see, it only comes to about 5% of the mass of the universe. So what exactly is our universe made of? And if we can't see more things, how do we know that they're there? And the thing that we do is that we look at the behavior of the things that we can see to figure out what else there must be there. Okay. And so we did know before Hubble that we couldn't see everything that was there. Here's another beautiful picture. This is the Coma cluster of galaxies, one of the densest cluster of galaxies. Each of these individual galaxies contains billions of stars, just like our own Milky Way does. And Coma is an extremely important cluster of galaxies historically. It was studied by this guy, Fritz Zwicky. I recommend going and look him up because he did some very interesting, cool research. He was a kind of a unique guy. He thought of things way before anybody else does. He was an astronomer at Caltech in the early 20th century, and he was a pioneer for much of modern astronomy. In the 1930s, he studied the motions of galaxies within this coma cluster. And he realized that the galaxies didn't behave in the way that they should as they moved from the mass that he could see. He thought the galaxies should be flying out. He didn't understand why this cluster of galaxies was still there. Why hadn't they streamed out and moved, since they were moving too fast relative to each other? And so he said that this cluster, in addition to all of the other luminous galaxies that we see, must be filled with some other dark matter that we can't see that had a gravitational pull on all of those galaxies. And so he was the first person to say that in between galaxies, there must be some kind of dark matter. But it turns out you don't need to look at clusters of galaxies to figure this out. You can also look at individual galaxies. And one way to think about this is if you have a string with a ball and you swing it around in a circle, it would go really fast in the middle. And if you made the string longer, the ball would slow down as it got further away. And you would think that this would happen in the galaxy as well. The stars in the middle should be rotating really fast, and the stars on the edge should be slowing down. But it's actually not what we see at all. Here is Vera Rubin. In the early 1970s, she was at Carnegie working. They took a big survey of lots of different galaxies and looked at how stars moved around the galaxies. And here's what they saw. This is what should happen. Stars should speed up, and then they should slow down as you get further away from the galaxy. But what actually happened is the velocity stayed flat further out. So the stars at the edge of the galaxy are rotating at the same speed as the stars in the middle. So there must be more mass than we can see in order to keep these stars rotating. And so that's the evidence for dark matter. Okay, so we can fill in another part of our universe pie. We know that 5% is things that we can't see. 27% is things that we can't see. Dark matter, we don't know what it is still. People are working to figure it out. There's some experiments to do direct detection, some underground mines where they're trying to detect these particles. But really, we can only measure it by measuring the effect that it has on the things that we can see. And I'm going to use that concept to try to explain dark energy. Okay, the next part of this puzzle involves supernovae. Here's an image of Messier 96. This is about 31 million light years away in the constellation of Leo. Here it is in 1997, and here it is in 1998. And you can look, and you can see that something's happened. There was a supernovae. And so a supernova is basically an explosion in space caused by either a dying star or an exploding white dwarf galaxy. And the reason that we care so much about these supernovae is that we can use them as standard candles. Their brightness is directly related to their distance away from us. And so just like when you're on the freeway and you see car headlights, they get dimmer the further away they are, you can relate their brightness to their distance. And here's a picture to show this. Their distance is a different brightness compared to where they are. And so because they all explode at the same mass, they should be pretty much the same no matter where they occur in our universe, and we use them as standard candles. Now, supernovae aren't very common. In galaxies like ours, we only expect to see about 2 or 3 every century. Here's a recent one that was studied in M101. We actually got data with this with our telescope, some spectroscopic data with DESI. And so they do happen a few times per galaxy. But if you remember, there are a lot of galaxies in our universe. And so from the galaxies that we observe, we can expect to see a few hundred supernovae every year. We just need to be able to catch them exploding. And so in the 1990s, 2 teams tried to do this. They captured supernovae data from as many objects as they could, and they wanted to prove that the universe was expanding. There was one team led by Sol Perlmutter and one team led by Rees and Schmidt. But what they found was something surprising. They found that the universe was expanding by looking at these standard candles over time. But what they found was that the expansion was accelerating. The expansion of the universe was getting faster. And so what could be causing that? There must be some energy pushing the universe apart. They don't know what it is, so they call it dark energy. Just like we don't know what dark matter is, so we don't know what this thing is, so we call it dark. This energy, we don't know what it is. We can see its effect of galaxies moving apart. We call it dark energy. And so for that accelerated expansion, they won the Nobel Prize. And so we get to complete the final part of our universe composition. We know that there's this thing called dark energy. It has a huge impact on our universe. It makes up about 70% of our universe. But what is it? So far, what we can say about dark energy, so it's the name that we give to the phenomena causing the acceleration of the universe. We can't directly measure dark energy. We can't see it. It doesn't have a gravitational pull. There are lots of possibilities and ideas about what it could be. Is it a cosmological constant? Is it dynamic? Does it change over time? Is it a breakdown of general relativity on cosmic scales? Are there some extra dimensions that we don't know about? Or is it something else entirely? And so there's new papers every week with a new theory about what dark energy can be. But the only thing that we can use to differentiate between these theories is more data. And so this is the data. I'm sorry it's so bright. Okay, so this is the data that we have from the supernovas. You've got time on your x-axis. This is us now. This is the past. This is the future. And we've got the size of the universe on the y-axis. And so as the universe grows, it's going to keep expanding in the same way. It's going to accelerate, or it's going to decrease. These dots are the supernovae. The lines are all of these different models, and you can see from the supernovae data, the little dots. The lines are the error bars. Using that data, you can't determine which of these type of universe that we're on, especially as you get further back in time. The error bars are just too big. We can't use supernovae to figure out what type of universe we're in. But it turns out there's another method. There's this method called baryon acoustic oscillations, which my 5-year-old very much enjoys saying. And so before we get into the details of it, one way that I like to think about it is like ripples on a pond. If you throw a pebble into a pond and make some ripples, and then you freeze the pond, you can go back at any point in the future, and you might learn how deep the pond is, what it's made of. You can learn lots of things from how these ripples formed. This is exactly what we do with baryon acoustic oscillations. So baryon just means matter, acoustic means sound, and oscillations mean wave. And so in the very early universe, before anything had combined together, there was these small bits of matter which would clump, they would grab on together, and then the energy density would push it apart, it would collapse again. You'd get these kind of oscillations in the matter in the early universe until it grew so big that it cooled down, that those oscillations had to stop. These ripples were frozen into space-time, and then as galaxies formed, they were predominantly gathered to these ripples, and matter formed predominantly on these scales of ripples. It's a weird concept. But, okay, galaxies clump in non-random way, guided by this natural scale, this BAO imprint. And this is what we're trying to measure. And so here's a way of looking at it. You take one slice in time of the universe, you find one galaxy, and you say, what is the average separation to the next galaxy? And that gives you some ruler that you can measure. You can take another slice in time, you can pick a galaxy, and you can say, what's the average separation to its neighbor? And you make another measurement. By making these measurements at different times, you can go all the way back to the early universe and get a measure of how this ruler is stretched over time, which directly gives you a measure of how much dark energy there is. And so because you're looking at galaxies and their neighbors, the more galaxies you have, the better statistics you have. Remember I showed you that plot with the error bars? We want to try and shrink those error bars so that we can differentiate between those different models. And so with DESI, we plan to measure the age of 40 million galaxies. To give you some idea of scale, this is one of the very first galaxy surveys that was ever completed. This is the CFA Redshift survey in 1977. Every single one of these dots is a galaxy. One of the things that I like is that you can kind of see some voids and some structure in the structure of galaxies. The cosmos is this kind of spongy structure that gathers on different scales. This contains 1,100 galaxies. The next big survey to do this was the Sloan Digital Sky Survey. This is their data. So we're in the middle. You travel back in time by going out. Each dot is a galaxy. Again, you can see these filaments and structures, this universe structure. The black patches are because we have dust in our Milky Way that we can't see out of. And so to give you another explanation of what we do, if we look at all of these galaxies and we say, what is the separation and how often does it happen? We can say there's more separation on a certain scale, and this is our baryon acoustic oscillation peak that we're looking for from the very early universe. So looking at the separation of galaxies, we learn about this BAO in the very early universe. This Sloan Digital Sky Survey, this is their actual data. They collect data from different types of samples. All of these different boxes are different types of galaxies, luminous red galaxies, quasars, emission line galaxies. This is redshift, so this is age. And this on the y-axis is the standard model of cosmology. So if the standard model of cosmology is correct, all of this data should lie on this line of 1. You can see it kind of does within the error bars, but there's a bit of kind of pulling it around. And so what we want to do is measure more galaxies to figure out exactly what's going on along this standard model of cosmology. Okay, how do we measure 40 million galaxies? It sounds like a lot. We could get a bigger telescope, which would collect more light, so we could look at fainter objects. We could do more multiplexing. This means that we can look at more objects in any single observation. We could get better detectors with lower signal to noise. This means that we have better efficiency and we can see fainter objects. The method that we used was more multiplexing. We wanted to look at more objects in a single observation. So how do we do it? Step 1 is you have to find your own telescope. And so the big telescopes, the 8, 10-meter telescopes in Hawaii and in Chile, lots of observers want to use them for different types of science. And so when you want to apply for time, there's all different types of instruments that you can kind of use. And so we don't want to do that. We want to have all of the time on a telescope. And so we found a telescope that nobody was using anymore. This is the Mail telescope, about 50 miles southwest of Tucson in Arizona. It got its first light in 1973, and at the time it was the second largest telescope in the world. It's got a 4-meter primary mirror, which is big, but not as big as people want to be using now. One good thing about this telescope, you might see it's built like a battleship. It's got a moving weight of 150,000 pounds, which is about 8 African elephants. And for people not used to looking at these big telescopes, the 4-meter mirror is there, kind of in the middle of that white block, in the middle of the telescope. So you can see the scale of how huge this telescope is. Okay, so we found a telescope, and they agreed that we could use it for about 5 years. The next thing we want to do is we want to give it a big field of view. And so the Mail's got a 4-meter primary mirror, but it's essentially just a light bucket. The real power of the instrument is what we put on it, what the light hits after it hits that primary mirror. And so we put this huge lens system at the top of the telescope. We put 6 lenses that were about 1 meter in diameter to make a prime focus correction. And that means that if you looked at the moon, you could fit about 6 moon diameters across the patch of sky we can see with a single pointing. This gives you some idea of the scale. Those 6 lenses are mounted in a barrel. These are some of the engineers that worked on this system. We have a hexapod to very carefully position these lenses, focus them, tip tilt, get everything perfect. Here's the lens system being installed. This black prime focus corrector in this ring. Everybody was on staff this day because everybody was so excited at this huge big lens system being craned up into the air very slowly and placed at the top of this huge big telescope. It actually had to be entered in through the slit of the telescope because it didn't fit in any other part of the building. We had to crane it in through the window. And one really cool thing about this corrector is that not only can you see a huge patch of sky in one go, we can move the telescope around to a lot of different elevations and still get light. And so just like at sunset, all of your light spreads out, you see red light spread out. That's not good when you're trying to make careful measurements. One of the really neat things about this corrector is it has two lenses that rotate against each other and correct the chromatic aberrations that you get as you point towards the horizon. So not only do we see a big patch of sky, but we can see a lot of patches of sky at the same time. Here's a picture to show this. So those two lenses, the atmospheric dispersion correctors, if they didn't exist, all of your light would be spread out into the colors. If you have those two lenses and you oppose what the atmosphere is doing, then you don't get any color corrections to make up for. Here's the light path. The light comes from the galaxies, hits the primary mirror, goes through this corrector, 6 lenses, 1 meter in diameter, and focuses on the back focal surface. Here's our very first image that we took with the galaxy, with the commissioning camera. It's the M51 galaxy, which is the very first galaxy that the telescope imaged in 1977. And this was kind of the first time that we knew this instrument was going to work. You know, we'd been building this instrument for 5 years almost, and we put it on sky, and we got this beautiful image, and the seeing was perfect, and it was kind of a really exciting moment that this instrument was going to work. But we don't have a camera on DESI. We aren't just making pretty pictures. We actually want to get spectra of these galaxies to figure out how old they are. And so this is where the multiplexing part comes in. We want to capture as many objects as possible. And so to do this, we place 5,000 optical fibers on our focal plane. An optical fiber is a strand of glass about the size of a human hair. And so you're getting light from an entire galaxy down a strand of glass the size of your hair. That's why this corrector needs to be so powerful. And these optical fibers we mount in individual robots. These robots move the fibers under the target within 2 minutes, position all 5,000, let us observe them for as long as we need to, and then 2 minutes later, we're able to acquire 5,000 more objects. Here's a movie showing how they move. The blue dots are the optical fibers back illuminated. They do these 2 rotations. This is real time. They move really quickly and really accurately. They position the fibers to within 5 microns. And so they do this all night from 6 p.m. till 6 a.m., collecting light from 5,000 galaxies every pointing. We normally get between 20 and 40 pointings per night. That averages to about 2 million objects that we get every month. So we really march along. We took Christmas off this year because it was full moon. Here's what those positioners look like. It's kind of like a pen. The fiber runs through the middle of the positioner. The main axis rotates 360 degrees. The phi arm rotates 180 degrees. And so from doing those 2 rotations, you can position the fiber anywhere within a 10 millimeter position. Okay, yeah, so we get about 10 hours of observations every night. 33 times 5,000 is about 165,000 objects every single night. Okay, so we've captured all of these objects. What do we do with them next? Next, we have to read the fingerprint. And so every object has a unique output of light, kind of like a fingerprint. When you split this light out by wavelength or get its spectra, you can learn things about it, like its metallicity or like its age. This is the image on one of our cameras. The 500 fibers go along in X, and wavelength goes along in Y. You can see some bright lines from the sky and some cosmic rays, but what we really care about is this. This is an oxygen doublet. It's kind of one of the pieces of the fingerprint that we know exactly what it should look like. And so from looking at what color it's at, we can figure out what age the galaxy is. This looks really messy, But when we put it through our data reduction pipeline, this is one fiber, all of the different colors of light. There's those two strips of this oxygen doublet. We can figure out exactly how old this galaxy is. This is a redshift 1 galaxy. And so then we can put all of these galaxies into these different age bins, see how our ruler's stretched, and get a measure of the cosmic microwave background. This is what those cameras look like. 10 cameras in a room at the base of the telescope, all cryogenically cooled. Each camera has 3 different colors, red, blue, and near infrared. I won't walk you through the spectrograph design, but if you'd like any questions afterwards, we can go back to it. We've got some nice detectors, and we've got some volume phase holograph transmission gratings. So here's how the photons go through the telescope. They hit the primary mirror, they go up to the prime focus corrector, they land at the back of the focal plane, where we collect all 5,000 objects. The fiber system routes that galaxy light from the top of the telescope all the way to the bottom, to the spectrograph room, which is kind of there, hits the cameras, spreads out into the colors, gets some wavelength. And it's been really exciting. In November 2021 alone, DESI got 2.5 million galaxies. 7 months later, we'd already made the largest map of the universe that had ever been made. 8 million galaxies, or only 10% of our survey. And last night, I checked this morning, we've collected 44.2 million unique spectra over 717 nights. We made some press. DESI creates the largest, most detailed map of the universe ever. It's all very exciting. In the first few months of data, we made our first detection of this baryon acoustic oscillation signal using only 2 months of data. This was published in April 2023. In April 2024, we released our year 1 data. And if you looked at the paper archive, tons of papers came out. But the real excitement was in the New York Times, a tantalizing hint that astronomers got dark energy wrong. And one of the cool things is this is our actual data. We kind of superimposed the shapes of galaxies to make it look more cool, but every single dot that you see here is a fly-through of a galaxy that DESI measured. And so, what exactly did we get wrong? So I'm going to go back to this plot. This is the same one that I showed you from the Sloan survey, where you're doing look-back time compared to the standard model of cosmology. And you can see with these different types of galaxies that we're targeting, one is the standard model. Even within our error bars, there's some tension that we're pulling us away from the standard model of cosmology. Standard model of cosmology is that dark energy is constant over time. And so this is implying that dark energy is changing over time. And you'll notice DESI follows a dark energy model that has 2 components, one that is standard and one that changes. So the dark energy equation of state, omega would equal -1 for standard cosmology. If we instead allow for 2 parameters where it changes and it doesn't, you have this pressure that's kind of pulsating and changing, we get a better fit to our model. This is kind of a more technical way of looking at the data. This is dark energy that doesn't change on the x-axis and dark energy that does change on the y-axis. If it was a standard model, we'd be at -1 and 0. But the data is kind of pulling us away from that -1. It's pulling us to a value that we have to have some changing amount of dark energy with time. Why should you care? And so aside from the fact that you can generate some really crazy AI images, when you ask what the fate of the universe is, will it end in a big rip, which would look exactly like this? This kind of changing dark energy with time implies that the universe might end up back in a Big Bang. Maybe we're in this oscillating universe of Big Bang, accelerated expansion, and then collapse. I'll give you a caveat that this data that was published in the New York Times is only the first year of data. With the statistics that we have, it's about a 1 in 400 chance that the data is wrong. Maybe there's some systematics that we need to figure out. The year 3 data will come out next year. It'll be really exciting. But the answer is we really don't know what the universe looks like. But I think it's really exciting that we're able to ask these big questions of the universe. And it doesn't answer them, but it gives us some clues that it's up to us to be able to understand these clues and figure out what's going on. And so thank you for your time. There's a really cool planetarium video available on YouTube. The movie is called 5,000 Eyes, made by some scientists in our group. And yeah, I'll take any questions. Thank you. Yeah.
So in one of the slides you mentioned that you measure in the future and also measure data in the past.
We only measure in the past. And then we use that data to extrapolate what the models would look like in the future.
But let's say light is coming today
Yeah.
in the lens.
Yeah.
How it can be in the past?
Because it takes time to get to us. The universe is so big. It takes so long for the light to get to us that, the light that we're seeing now is from a long time ago.
I know, but how can you go back, let's say a star is coming,
Mm-hmm.
it's like a billion year, then 90 away. So how can you go back to 2 billion light years? What is the reason?
It's because of how big the universe is and how long it takes to get to us. And so one way that people think about it is when a fire truck goes past you and you hear the siren, and when it's close to you, the siren's one frequency, and when it's further away from you, it's a lower frequency. It's been stretched out, right? And so from that change in tone, you can measure how far away it is. And so just like the light from the stars, it gets stretched as it travels to us. That stretching from what color it should be to what color it is allows you to measure how old it is when you get it. Mm-hmm. Yeah. So one nice thing about having optical fibers is that you can put your spectrographs and detectors in a different room on the ground floor, and so it can be really stable. And so we control for humidity, for temperature, for gravity. Everything has to be so precise that if you use optical fibers to take the galaxy light from this telescope that's moving around and flopping around to this really stable camera, you get a much more stable result. Positioning. So you've got, you've got 5,000 fibers on a 1 meter focal plane. There's big gaps between it. And so the galaxies don't fall everywhere. So before we went on Sky, we did a big imaging survey to figure out where all the galaxies are that we want to look at. And then we've got a really efficient system which says what's the best order to look at those galaxies. And so the fibers get a command that says, hey, you want to be at this position. The robot moves them, gets it exactly where the galaxy is, and then we're able to detect it. Mm-hmm. I mean, if you had unlimited detector space, you would just tile the entire focal plane with fibers and route them all down. But we don't. Mm-hmm. Yeah.
When you say dark energy is oscillating, does that mean like it's increasing and decreasing, or
it's changing with time. That's all we can say right now, right? So here, this is the look back time, and so where we are is 0, and then further away, it matches what we expect from standard model, but there's this point in time where it's not what it should be. It's pulling us away. And so what we expected was that all of this data would fall along this line of 1. Everything matches standard, but the fact that it's pulling us down, not everywhere, only at certain ages, means that it must be changing with time. Mm-hmm. Yeah.
Hi, thanks for the presentation. I was wondering, do people need to be constantly physically present, with the telescope, at all times someone needs to be there?
Yeah, so the way we set it up originally, that was definitely the plan. And when we started observing, it was 5 people in the control room every night. It was really exciting. And then it was March 2020, and we couldn't do that anymore. And so we quickly pivoted to a model where we could remotely access the telescope. And so we have one person there, to hit the big red button if it all goes wrong. But we can do everything remotely. It's amazing. And I think more and more telescope sites are moving to remote observing. All of the Hawaii telescopes, because it's such an inhospitable place, are all remote. But it's really fun going to telescope at least once. But it's pretty convenient to be able to be home and observe from home. Mm-hmm.
And do you get a lot of interference? How many things is the data good?
So we tried it. People choose telescope sites by the quality of the seeing, so how stable the air is, and by the weather. And so I think on Kitt Peak, where this telescope is, I think we expect to lose about 30% of the year to weather, especially in the monsoon season in the summer. The other big thing is light pollution. So the 2 closest places to Kitt Peak are Tucson and Phoenix. Tucson's really close, but there's lots of programs where people have, helped change the street lights and point them down and have different frequencies. And so we don't get a lot of light pollution from Tucson. We get a ton of light pollution from Phoenix. Yeah, but it's pretty miserable when you travel all the way to Tucson and then you go up to observe and it's raining and it's thundering and yeah. And we also don't observe very much during a full moon. It just makes the sky too bright. And we do engineering time where we, change the detector or fix something that's broken. And yeah. I think the downtime here is more. Yeah. Maybe get my weather. Yeah.
You've now got results for about 2.5 years in?
3.5. Yeah.
I'm just curious, are you planning to do this particular experiment for much longer, or do you also have other plans for this?
So, kind of the more data you get, the more things you realize that you haven't quite done properly, or the more things that you want to figure out. And so there's already plans with this instrument to do fainter objects, bluer objects, try to really get more early universe physics rather than later galaxies. People are proposing this type of instrument, but on a bigger telescope. Everybody always wants a bigger mirror. And more fibers, bigger mirrors, more fibers. And yeah, it's really productive science. It's a very big collaboration. There's about 800 people in the collaboration. And another cool thing that we do with the data is it's a thing called blinding. And so we get all of the galaxies, but we put some extra thing in the data that nobody else knows about. And so when they do all of the analysis, they can't kind of massage the data to get what they want because there's this extra parameter that they don't know about. And so they do all of their analysis, they give all of their code, and then we unblind it and they're not allowed to change anything. And so the answer you get is very kind of unaffected by what they expect to get from it. Yeah. Totally, yeah. They can't say, hey, you know what, we should have made the cut here, and yeah. It's kind of a good way of keeping yourself honest in this huge collaboration. Mm-hmm. Yeah.
You mentioned a lot about trying to measure how much of dark energy there is and how much force it exerts. Do we have any clues on what exactly is made of? Could it be an undiscovered particle? Could it be a force?
I think it's some kind of fundamental force. We have our 4 fundamental forces, and then there's this other, it's kind of like an anti-gravity force. I am not a theorist. Yeah, there's lots of competing things. I think some kind of anti-gravitational force might be the forerunner, but yeah.
Any chance someone could discover something like this?
I mean, it's not going to be a direct discovery, right? It's going to be which idea fits the data better. And so we just have to keep on getting more data and spread it out over as many timescales as we can to understand it. Yeah. We might get a dark matter direct detection, but we won't with this. It's good branding, though. Yeah.
So, where is closest dark matter from here? can you just get like?
It's everywhere. It's everywhere. Dark matter's everywhere.
So, and you say it's everywhere, but we cannot prove that it's not matter.
It's some kind of antimatter, right? It's dark matter is some kind of antimatter, some kind of particle that is very weakly interacting. We call it cold dark matter because it doesn't interact very well with normal things, which is why we have to have these big tanks, you know, in a big mine shaft with nothing else around, trying to get some kind of detection of this very weakly interacting particle.
So what you're saying, so you can do it here?
Dark matter. Yeah.
So
And people are.
dark matter, you can do it like on
People are doing it.
okay.
Yeah, there's some mines in Idaho, Iowa, one of those two. Yeah.
So it's like here?
Mm-hmm. Everywhere.
Okay,
Yeah.
smell it.
Yeah, let me know if you find it.
Is there any prize for this?
I'm sure there is. It might be a nice big gold medal. Yeah.
One of the theories that you had up there was that the issue is that general relativity breaks down on a cosmic scale. What would the data look like in order for that theory to be true?
It would pull this data down just like it's doing. Yeah, that's exactly. It's exact. This is a 3 sigma result.